So we saw previously how the mechanism of attention could be incorporated into a sequence-to-sequence recurrent neural network, and that allowed the output at each time step of the decoder to pay different degrees of attention to each of the states of the encoder at different time steps. And this turns out to be very powerful and very useful. What we're going to do now is generalize that idea into a general purpose layer that's very, very powerful as a component that we can use within a neural network. So let's just lay out how this layer works. So it takes as input a query vector, Q, and previously when we were using this in the sequence-to-sequence scenario, that was the hidden state vectors from the decoder, so that was what the query was in this case. Next, it takes a set of input vectors, x1 to xnx, and previously those were the hidden state vectors from the encoder. So remember, those were the things that we were comparing against the query vector. And it also required a similarity function, FATT. And the computation for using this attention mechanism was first we compute similarities, so we compare the query vector against each of the input vectors using this similarity function. That gets us the similarity scores. We normalize them to attention weights using the softmax function, and then we compute the output of this process by using those attention weights to combine the input vectors to give us our final output. So we're now going to make a number of simplifications to this general idea. So the first is that we're going to replace the similarity function, which I previously said was learned with an MLP, with simply the dot product between the query vector and each of the input vectors. Dot product are really, really cheap to compute, and they prove to be sufficient for this purpose. In fact, we'll go slightly further than that. What's actually generally used is the scaled dot product. So all that means is we still use the dot product between the query and each of the input vectors, but we divide that dot product by the square root of the dimensionality of the query vector. And the rationale for this scaling is that it avoids the largest value completely saturating when we apply softmax. So if we apply softmax and one value is significantly larger than the rest, then after applying softmax, the other values will go almost to 0, and that one large value will go almost to 1, and then we get vanishing gradients. So this division sort of pulls everything back towards 0, and it kind of flattens out the output of the softmax. Right, the next simplification, or maybe better called generalization, is to allow multiple query vectors. So instead of just having a single input query vector, we'll input now a set of query vectors which we can store in this matrix Q. So we can also write our input vectors as a matrix X, and it's got this nice property that all of those dot product similarities can be computed in one go by just doing a matrix multiplication between the query vectors and the input vectors. So note that they have to have the same dimensionality, but we don't necessarily need to have the same number of those two things. And we still normalize all of those dot products. The rest of the process is still the same, so we still do softmax, but just noting that this thing's now a matrix, so we're doing it along a particular dimension, along basically like the column, so the second dimension, and then we can also compute the output, so that's the weighting and summing of the input vectors, again by just doing a matrix multiplication. So we now multiply the attention weight matrix by the input vectors, and that does all of those outputs in one matrix multiply. So this is really efficient. Matrix multiplications can be done very efficiently on a GPU, and that makes it ideal for use within a neural network. Now, note one important thing. The input vectors are used in two ways in this process. They're used once to compute the attention weights, so where we compare each of them against the query vectors to get us a dot product similarity. And then they're used again to compute the output vectors. So at this point, the output vectors are basically just weighted combinations of those input vectors. And in both cases, we're using the input vectors x. Now, this might not be desirable for a reason I'll explain in a moment. So that gets us to our next generalization or simplification, which is to separate the key and value. So we still have as input our query vectors in the matrix, our input vectors in a matrix. But now we also have two matrices, a key matrix and a value matrix. And these are used to transform the input x in two different ways. So the key matrix transforms the input vectors into the keys, k, and the value matrix transforms the input vectors x into the value vectors, v. And now in the computation, we use these two things in two different places. So when we're computing the similarities, we use the keys, and when we're computing the outputs, we use the values. Now, if you think of this process as being a little bit like retrieval, then it makes sense that you would want to use different things as your keys, so for looking up for similarity, as opposed to the things that you're actually retrieving the values. So let me give you an example. Imagine if you were searching Google for something like how old is York Minster. So that would be our query, and Google would be comparing that query to all of the web pages that it's got stored. And you can think of that being the role that's played by the key vectors. They let you find the matches. So Google is essentially looking for web pages whose key contains something similar to how old is York Minster. But I don't want Google to return the bit of the web page that says how old is York Minster. I don't actually want the thing that matched my query. What I want is the answer, and that's some different information from the web page. And that's the role played by these value vectors. So you can see that there might be a reason why you would want to use different information to do the kind of lookup, this compute the similarities, as opposed to doing the actual outputs of the retrieval, how those values are combined. And by doing this, we give the model more flexibility to use those input vectors in two different ways. So we've now arrived at the general formulation of an attention layer. So we usually write attention as being a function of query, keys, and values, where often keys and values are just derived from a set of input vectors with two different weight matrices. And the output is simply I get my attention weight by comparing all the queries against all the keys, and then doing scaled dot product similarity followed by softmax, and then I use those weights to recombine the value vectors to give me my outputs. Now there's a few special cases and additional details that need mentioning. So one special case is called self-attention, where the input vectors are the same as the queries. So we no longer have any input queries, we've only got input x. But because of that, we introduce a new query matrix, which we use exactly the same as we did for the key and value. So in the computation, we now, to get queries, keys, and values, we simply multiply x by those three different matrices, and then everything else is the same. So for similarities, we use the keys and the queries, and to compute the outputs, we use the attention weights and the values. Now, this self-attention layer has a very nice property. if we permute the input vectors, so if we reorder each of the set of vectors that we put into X, then the output is unchanged, it's just permuted in the same way. So what that means is this self-attention layer is permutation equivariant. So permute the input and you'll just permute the output. One other way of thinking about this is that the self-attention layer doesn't care about the order of its inputs. Or another way of putting it, it doesn't even know the order of its inputs because its computation is unaffected by the order. So this is a useful property, but we'll also see in a moment you might need to take special care with this. So I've called this special case self-attention, but actually self-attention is so common that sometimes we refer to normal attention, where the queries are not the same as the input vectors, as cross-attention to make this difference clear. So we've just said that the self-attention layer doesn't know the order of its inputs. Now this could be a problem because it would see no difference between, for example, the input sequence "we are eating bread" and "bread are eating we," which clearly has a very different meaning. So a kind of hack is used to make self-attention position aware. So what we do is we concatenate each of the input vectors with something called a positional encoding. So if x1 is going to be my first input and we would like the self-attention layer to know that it's the first input, then we're going to take the value 1, because this is my first input, pass it through this positional encoding function gamma, and then whatever vector this returns, we're just going to tack it on the end of x1, and that becomes the x1 we actually feed to the self-attention layer. For the second input we do the same, just positionally encoding the value 2 this time. So this positional encoding function gamma is either a fixed function that just does something to those positions to give you a vector, or it can also be learnt, so you just have a learnt embedding associated with each input position. Okay, I'm going to finish up with two more special cases which are quite important in practice. So one is called masked self-attention. So the idea here is to not let vectors look ahead to information that's coming in the sequence. This is really important in language modeling, where you're asking the model to predict the next word as its task. So for example here, when we input this first token, which is just the start token, the attention weight is, or the attention score is set to -infinity for the positions that haven't happened yet. So when we're at this first token, we haven't seen the second and third token yet, so we're not allowed to pay any attention to them. So there would only be a value, a similarity value for this the first position. So we'll end up with an attention weight of 1 and zeros in those other two positions, because the softmax of -infinity is just 0. When we're considering the second token, we're now allowed to pay attention to the first and second. So we're going to mask out one of the attention values. And so this procedure of inserting these -infinities into the similarity scores is called masked self-attention. And the last special case is called multi-head attention. This is a really simple generalization. And the idea is just to apply independent attention layers in parallel. So we're going to apply H of them. So the input is the same, it's just one set of queries, keys and values, but we'll pass each of those to H independent attention heads. We will concatenate them into one large set of output vectors, and then we'll use this learnable matrix WO to recombine them back into the single output vectors.